So now we're going to move on to chapter 6. So we introduced the concept of the precise specific regime. So sequence of the regimes, treatment regimes that has some consistency over time, right? So basically, it's a conceptual characterization of the feasible sets of the treatment. And then our goal is to find the optimal regime which maximizes the expected potential outcome of the regime. But notice that this D is a function of the potential outcomes, right? So D itself is a function of potential outcomes. So even though it may look like a univariate expectation, it is not, right? Because this D is a function of the potential outcomes. So we have actually a joint distribution of the potential outcomes. Okay. Now, the idea is we want to characterize the optimal regime in terms of the potential outcomes using the principle of the backward induction. So backward induction is how to find the optimal treatment regime when there's a sequence of decisions. So so far we just have a single decision, right? We consider a single decision. But now suppose you have a multiple decisions over time, then what is the fundamental principle in that situation? So turns out that this backward induction is a concept in the game theory in economics. So in the game theory, how you want to so if the enemy does this, then I should do this, something like that, right? So it's kind of based on the two-party situation. I mean, could be multiple, but anyway. But the idea is that we'll see what backward induction is. But the interesting part is that in econometrics, the loss function or utility function is a known function of the parameters. I mean, so the objective function, the utility function is a function of the actions, but the parameters are treated as known, right? But here, we are going to use the data to estimate the parameters in the utility function. So that's actually very important part, right? Because game theory is mostly focused on how you optimize given the utility function. But here we are not just optimize, but also estimate, learning, right? And then the second step is this is the finding the optimal treatment regime in terms of the potential outcomes. The second step is find the optimal treatment regime in terms of the observed data. So it's like a identification kind of so we have the same issue. And then third part is how we actually some form characterization of the estimation method. Okay.
So, can you please explain a little bit what is precise specific regimes in the first line? Yeah, so
that is actually kind of we covered in the previous class, right? So yeah. No, not the previous class. Actually, maybe the previous one. All the way. Yeah, I can see. It's basically feasible sets, right? Feasible set of the options. Yeah, I mean, there's some. I don't have a good real example, but for each given the current condition, the doctors may have different options, right? Options of choice. So then conceptually, this you have you can basically rather than so this is a history, right? From the history to options. So that is a big set, right? But for particular step, actually we may have a reduced possibility. So possible history, because you don't really have all passes, right? You just have a limited options, and then this is a subset of the A. So here's a kind of this is just a mathematical formulation to make it as a general statement, but the idea is not really critically important, I think. But anyway, we introduced the two concepts, right? The set of gamma and lambda. Gamma is the feasible set of history, and lambda is a history and the element history and the element in the feasible set. So this is gamma k contains all possible histories consist of having followed the precise specific regime through decision k-1, and lambda k is the set of all possible histories and associated options in psi k hk at decision k. And then so k is 1 to capital K, and then so decision is made in K steps, capital K steps. So K equal 1, we choose A1, right? We choose A1, and that basically gives determines X2. So A1 determines what you observe in X2, right? So then K equal K, you basically have a K, capital K. You now determine AK. That basically gives you what? So there's no, so okay, there's one way. You can view it as a K plus 1 star, which is we call Y star. So it's just a notation. So you assume we have a X1 XK, right? Star. And then X1 X2 star, right? So X1 X2 star and XK star, and then Y star. So that you first one determines X2, right? So K1 determines K-1 determines XK star, and K1 determines Y. So that is this. And so the gamma K then, so notice that. So what do you mean by possible history? Possible means that its probability is positive, right? So this positive, so positive probability of the history means that it is possible, right? Same way, we have this one. So the y, this particular set of y should be positive, otherwise it's excluded. Okay. And then we are kind of restricting our attention to those with the domain gamma k to ak, where and then this one should be precise specific. Okay. So this is just a formulation, right? And then, so the goal is to characterize the optimal regime such that this one works. and secondly, we want to estimate it from the observed data. Okay. First remark is that the possible set, right? This one, this property is written in terms of the potential outcome, can be expressed as a property in terms of the observed one, right? That is basically the G formula. Same way, our probability here was written in terms of the potential outcomes, but it is now written in terms of the observed wise. Okay, observed data. Okay, now this is just a setup, right? We just introduced the remind the notation, and now we wanna do some really solve the problem. Okay, so first step is we wish to characterize the optimal regime in terms of the baseline information x1 and potential outcomes W star, where W star is actually whole vector of the potential outcomes, right? Potential x and y star. So y in reinforcement learning, we call this as a state, and we call this as a reward. So that's the same concept, but basically y plays the role of evaluating your utility, right? So y is plays the role of evaluating your utility in the sense that you make the decision based on the expected reward, right? So that's the so basically you want to make a right your decision criteria. Your decision criteria is based on y. Okay. However, how you obtain your y star depends on x, right? Okay. So I like to so we'll use k equal 2 because that is simplest without losing the key ideas, right? So we, k equal 2 to illustrate the idea of the main idea. So in k equal 2, that means we want to do make a decision twice, right? So 2 times d1 d2. So backward so the big idea. So the keyword is the backward induction, backward inductive method. So basically we as a human being, right? We make the decision not in the backward, right? We make decision forward way. We just choose over time, right? But then later you regret, right? Because you later you realize that you could choose better way, right? But it's too late already because your decision has already passed in the past. So you cannot really reverse your decision, right? So then what should we do? Well, why don't we make the decision backward from the future to the present, then you can always go back, right? Because you haven't really did the decision yet. So that is the basic idea. So the backward induction, okay, because you basically find the optimal decision at t equal 2 as a function of all the previous history. So this is basically the history at time 2, right? But this is kind of remained open, right? You have a flexibility as you leave it, and then you optimize. And so that you can plug in this one to here, then you actually find the optimal. Okay, so the optimal, so we already know that for the single decision, right? For a single decision, we know how to find the best optimal decision by just maximizing the Q function. So Q function is nothing but the expected reward conditional on the history. Okay. So in this case, in y, in term for y, the conditional on suppose we know this potential outcome x variable, then this is basically function of x1, x2, a1, a2. And then we at decision 2, at time 2, we just choose this one. Leave everything as a given. Okay, x1. So it is actually conditional. So basically this is a function of all the previous history. Huh? Where?
Yes.
Here? We have a function. Huh? Based on history, right? Function of history. I'll use an example to illustrate soon, but this is.
But this cannot be applied for the reinforcement learning.
Huh?
Can this be applied for reinforcement learning?
Well, I don't know. Because reinforcement learning, so basically this is all the things are assume that you know the cue, right? So in the reinforcement learning, you can still do that. That is a exploitation step, but you still want to explore. So then the uncertainty.
Right. So this approach is because we do backwards, right?
Right.
It's because we have the full sequence of data.
Right.
Right. So for each step we
Right.
have already observed. So when we design, we can think what is the best choice to do backwards. Like profile maximization.
Okay.
Yeah, but for reinforcement learning, for online case, we do not have data for the future. We kind of have to do this optimization step by step.
I see.
Yeah, I also don't know.
Okay. That's a good point, right? So we don't have any data for the future, right? Yeah, that's right. So that's right. So I think I don't know much, but it uses the Markov assumption. So some kind of a Markov step period assumption, so that your transition is actually can be learned from the current data, something like that.
I think for now, if we use backward, it is more like dynamic programming.
That's right, dynamic. So that's right. So it's actually a stochastic version of dynamic programming, right? Yes, that's correct. Yeah. And then now we plug in, right? So we use, so now once the two is chosen, then the expected outcome becomes a function of A1. So this is the value function based on the history. And then you now So this guy is nothing but Q2 and evaluated at the maximum. So you choose A2. So this is the best A2 hat, something like that. So best A2. The plugin that basically is the optimum of the Q function, right? Q2 function. And so then now you view it as a function of A1. View the whole thing as a function of A1. And then optimize over A1 to get T1. Okay.
So what is Q2 wise
Yeah. So Q2, so yeah, so notation is a little bit messy, but yeah, so Q2, use Q2 to and then plug in to get a V2 and then take the conditional expectation of Q. So this one becomes a Q1, AX1 and A1. And then you basically maximize over A1 to get D1.
So in the previous Q2, we assume that if we go to the previous page,
Okay.
we assume that X2 star can be observed. X2 star. can be
You mean
observed.
this one?
Yeah.
So that is the first step. We first characterize in terms of potential outcomes. So later we will move on how we can actually compute it, because we don't really observe this one. But for now we express, so because this is the, suppose I know this Q2, then this is the solution. So yeah. Yes.
Define the sign to
Which page should I go look at? This page, okay?
space, right?
Right.
And this space is defined with the forward. Stack.
So
We define sign to depending on the previous state.
so this one is a given. So this is given, right? So this one is actually H2. So as a function of H2, I know the feasible sets. Okay. And then among these feasible set, I choose the one that maximizes this Q2.
Okay, this is a complicated.
Yeah.
Because your space actually changes when your argument changes.
Right. Yeah.
Now, but H2, right? H2 is defined based on the observed data.
Actually, this is actually a function of the possible history.
Right, but it's observed.
No, well, possible history means we know that the possible history is actually written as a. So here you can basically, so you are thinking of this way, but my point is that actually we are talking about here. So this possible history is written in terms of the potential outcomes.
It's K bar observed, right?
So this is observed. I mean, this is not really a random variable. This is the kind of the possible value has a positive mass. So it's kind of
Since you're talking like Jae-kwang to estimate the potential outcome, and is it still?
well,
Are you using
okay.
the-
Let's probably go to this example. So this is the homework 5 example, right? You guys did due date is probably you guys already submitted it. So basically this is the you have a decision, right? X1, at the time, you using D1, you have this possibility. And then decision 2, you have this possibility. And this possibility. And then you now have a realized count. Okay. So then basically, because we later show that this Q2 is just this one. Conditional expectation of Y given observed axis. And so what do I mean by this? So that's what I'm trying to show you. Okay. So basically, so what do I mean by this? X1, X2, A1, A2. Basically, we have these four combination, right? X1, X2, A1, A2. Four combination. We just have a Q. We just have data. So we use this information to compute the Q function, Q2 function, which is this one. Okay. So what is the Q2 function? Basically, this is the Q2 is nothing but the expectation of the Y for given all possible combination. So that means we can actually, from the data, this is real simple toy example, but still you can at least estimate, right? The Q hat 2. So you can actually compute all this from using the data. And then my point is that here, what exactly means by this? It means we know that this is given X1, X2, A1. We just compare two functions for A2 equal to 1, A2 equal to 0, and compare and choose the one with the bigger Q hat. So in this case, they are equal, tied. So then it doesn't really matter. But here we know this one is better, right? Bigger. So that means our decision should be choosing this one. So that is why we get 1, 1. Okay. So same story here. So we know what is I kind of confused the first, but that's not right. So which one is bigger? You know that this one is bigger, right? So that means this one. So then here, different, right? We know that this one is bigger, so it should be 0. And then basically the winner takes all. Like locally, the winner takes this value so that you create the V2. Okay. And then once so basically at least the Q equal 2, I mean, at least the second decision, we know we have the optimal decision already for each combination, right? For each combination, we have this decision. And now what you want to do is to compute Q1 using V2 conditional expectation of V2 given X1 and A1. And so that basically means you can basically do the same thing here. So that's kind of and then basically you compare, right? So you use that to compute the Q hat 1, and then compare this Q between the two Q1s, right? And choose the one with the bigger value, right? That option, right? Because you have a A2, now we're gonna compare this actually. So anyway, something like that. Okay, so that's kind of a plan. So if I hope I can finish up until the actual computation, but there's some way to go. Okay, now, so basically these two, right? The description step 1 here is that what is the basic idea of the backward induction, right? So backward induction is to compute the optimal decision at 2 first and then do it 1, right? So here's a justification. So justification at using the k equal 2 situation. So basically we know we can write it as a indicator function. So you can see that this one as D2 thing is D2 depends on potential outcome. Right? So this is really a quite complicated random variable, but you can actually split D1 because it's an indicator. You can actually, right, make a product, and then move this one to here, and then take the summation of the A2 over and code it Y star A1 D2, where Y star A1 D2 is a function of A1, but D2 is a kind of a rule, right? The decision rule that we know already. So because this is what is the so given, right, for any, so that means for a given decision rule that depends on history, which is x1, x2, and a1, right? So given, so this is a known function, right? Given the known function, I can actually dynamically, right? So no matter whatever the potential outcome is, that will be put into my input to this function, so that end of the day we can write this. So now once you write this way, so that means this guy y star is the potential outcome for a1 equal to small a1 under decision 1, and a2 which is random because it depends on the potential outcome, right? So then now we're going to take the expectation. So expected potential outcome is, so then so this is expectation is actually expectation of the conditional expectation of the this given x1, something like that. So you actually x1 and x2 star a1 and a1, something like that, right? So you write this way, then this conditional expectation inside can be written as a sorry, this one is actually right. So because we treat D2 as fixed, so D2 is fixed. So so that this one becomes something like this. So actually, we don't really need the condition on this because this is in terms of potential. Okay. Huh? D2. Yeah. Conditional of this one given potential outcome. Potential outcome. D2 is a function of random variable, x1 and x2. Start. Okay. Yeah, so this D2 is fixed. The random variable changes. So we just do the conditional expectation given this random variable. Okay. So the conditional expectation is taken with respect to this potential outcome given, right? And then by the definition of the of this D2 optimal, we have this one. For any, which implies So which implies this, right? Because this is a expectation. So that is one result. So that is for all, right? So no matter what, so this is same, but we optimize only over D2, right? And now, yeah,
Using the same approach, we can show that the forward optimization is not optimal.
not optimal, right?
Right, so this, I think, can follow the same approach,
I see.
because it's, the essential step is the condition, right?
Okay.
So the past condition of the previous decision.
So right. So I guess we never know the optimal decision of D1 until we go to the future, right? So that's why we want to first optimize D2 and then optimize over D1 so that we know that it will eventually give the global optimum.
So my question is, why cannot we make that? Because we know X1 in the past tested, right? So why giving X1 now? We can use that, we can get the D1 optimal in the past tested as well by maximizing this Q function.
We have two decisions, right? So what is your question?
The question is that we can still get D1 optimal in the past tested because we need to.
We can't, right? No, because we don't know. I see. So you, okay. So how you are thinking? You are thinking of taking the conditional expectation of the what about A1? I mean D1, D2, given. Well, how you cannot really. No, you you don't. So for the way you cannot really achieve the optimum. It only so I guess it only you can, right? You can use consider, of course you can consider Q1 and you can of course achieve this one, right? You can achieve this one. This one implies this one, but what you really want is you choose. You want to choose this one to be optimal. Right? Because we want to, so basically we want to combine 1 and 2. And combine 1 and 2 to show global. I mean this one. So
I think here, probably the feasible set is important. Because if you think about when we're optimizing, right, a two-dimensional function, right? So we can profile each one, right? If the area of the covariance is kind of has unrestricted shape, right? Like a spiral, right? It's like a spiral, so then we can either profile over the x-axis,
right.
x1 axis, or profile over the x2 axis. But here that the feasible set depends on the feasible set of the second step depends on D1.
Right.
Right. So
that's right.
So we have to do backwards.
Backward, right? Exactly. That's the point. Right.
So yeah.
So right, that's good point, right? Thank you. So this one depends on A1. I mean, right? Depends on, so D2 depends on D1. So you cannot really So
Right, and then D2 is a function of D1. Ultimately, we're solving this problem. We are comparing two functions.
right. So we
We can
optimize.
always, yeah, we can always compare the two functions from the optimal decision. Given the codec.
I see.
So D1 is a function of the codec. Because, when we optimize D2, we are comparing two functions. A function of D1 is also a function of X2.
Right.
So essentially, we are comparing,
So you
based on
can
the
say
similarity, we can.
forward, as long as we can express the forward D1 as a function of X2, you can apply the same thing, right? That's the point, right? I see. Yeah, that makes sense. So I think the backward, we are kind of the setup is that we never really recall, go back to the past. So that's probably why. But the mathematically, your point is mathematically, what should make a local optimization, it should be depends on the others. So then you can first conditionally optimize and then optimize unconditionally, something like that. I mean, this is
For calculation, we're going forward because we use conditional on some D1 to given value D1 to calculate D2, but for choose the optimal path, we have to start from the last step to do that selection.
I see. That's right. Yeah, well, I think this is really clear to me, but somehow I cannot really.
I think in some cases, the forward and the backward probably are equivalent in terms of the maximization. If that's, think about, they have two choices for the first stage and two choices for the second stage. And we have all the four combinations, right? And we have all the four combinations. So then with maximization, we can first fix D2 and maximize D1.
Right, yeah, right. But I guess the stochastic nature, right? I think if the X2 star, because X2 star depends on X1, so the model that we assumes is this way. So that's why. Otherwise, we can still. I see your point. So later, we can of course do the forward optimization, but then you need this kind of a model, which does not make sense. So basically to compute, I guess the point is to compute this respect Q1. What you need to compute Q1, you need the conditional expectation of X2 given X1. That's a natural model because you want to model over the future based on the past, right? Rather than model over the past based on the future, right? So that's why because I mean mathematically it doesn't mean which direction you can still do that, but when it comes to the constructing the Q function, this is more natural. Good.
I think we think it as a like the hierarchical model in Bayesian estimation, it's still nature. I think for Bayesian, the sequence is that we first have parameters theta, and then we have conditional expectation of x given theta.
Right.
But in the estimating procedure, we still write the theta hat as a function of x.
Right.
Just because we change the their order in calculating the conditional expectation. So our theta hat is a function. The theta hat here is like the D2. No, D1. I mean D1 is a function of
I see.
D2.
Yeah. So
just like say had its functional X, but in fact, in reality, we first have say the prior of say and then we can have the distributed.
That's right, that's right, that's right.
If we think it as a hierarchical model, I think it's nature to change the order.
Okay, okay. Yeah. So yeah, I think there's a nice, interesting analogy with the base. So modeling and estimation, but here, so it's two. The estimation and decision. So I think
This can also be calculated based on Bayes' theory.
right. Actually, I have a proof right soon. Yeah. Okay. Well, let's move on. I think we are kind of spend too much time. So I guess my way, well, this is just a formal trying to, because basically the local optimization yeah, so basically it's kind of dynamic programming, but let's just move on. So here's a kind of sequential formula that how we actually do this optimization for many steps. So basically, you start from the very end, capital K, and because you observe Y, so you start with the observed Y, and then carry backward. So you start observe the Y. This is not really. You can actually later you can observe Y anyway. So that you basically use the model for Y to find the optimal decision in the end, and then use that to construct the best pseudo best value function, and then use the value function as a Y variable, as kind of a Y variable at that step, and then optimize, and then use that to obtain you update. So this is kind of back propagation, right? In the machine learning, in deep learning context, you basically so propagation and forward and backward, right? So because you have a Y in the very end, so you do it backward. Okay. So so this is kind of formulation in terms of the potential outcomes. And next step is to characterize in terms of the observed data. So the key idea is just this, right? So basically, this is the optimal decision in the end point, and then from K-1, K-2, so backward, right? You just choose the optimal one sequentially in the backward way. But in order to do that, you need to update your V value function using the conditional expectation, using the Q function, essentially. So the key part is how to compute this potential. So how to compute this conditional expectation in terms of the potential outcomes. Turns out that you can use the observed data to compute this Q function, right? So that is the identification part. And then use that to find the value function. Same way, once you have a value function, you can compute the conditional expectation given the previous step, potential outcome, and then optimize over AK to obtain AK to obtain the optimal decision at case step. This is a special case. So you in the backward inductive backward induction to compute the optimal decision at k equal to 1, then this guy actually will be used to here, right? Because your decision depends on A. So this one is a conditional on A, but you don't know which one is one. So you use this one and then forward, right? Here's some important so this kind of equality, it has been introduced a few times, but I didn't really. So I'd like to explain this one more time. So basically, the first term is in terms of the potential outcome, while the second term is in terms of the observed one. So that intuitively, right? Intuitively, the conditional on the potential outcome and conditional on the observed, these two events are equivalent. Why? Because this one means this one is the potential outcome for this particular choice of A, which is equivalent to the observed outcome, observed one, and the information that AK is this one, right? So that is that intuitively makes sense, but we never really prove it. So I'd like to prove it.
The V can be any function, right?
Yeah, any function, right? That's right. Yeah.
Yes.
So that's right. So what we are going to show. Okay, so we are now in a position to show this. So what we want to show is the probability of xk star, right? AK given x bar k a bar k minus 1 equal x bar k is equal to probability xk plus 1 given x bar k equal x bar k and a bar k equal to a bar k. Right? This is what we want to show. So basically, if you can show that, that basically means what? Whatever the conditional expectation written in terms of potential outcomes can be completely expressed by the corresponding conditional expectation in terms of the observed data. That is the key idea of the essence of the G formula, right? So here's a proof. Okay. So when we try to prove it, don't start with this. You should start with this one, because start with the complex one to simple one, right? Rather than from simple to complex, it's impossible. It's like a water flow trying to go upward. That's not possible. So we use this one. now see what's going on. First of all, the first equality is clear, right? Because given this information, I know by Stuba, this one is equal to this, right? That's a Stuba. And the second equality is just the base, right? I just use the base theorem.
So the second one should be A bar, right?
No, I actually, so see, this one is A bar, but this one is single AK.
I mean, the second equation, X star K plus one, A bar K.
This one.
Yeah.
I see. You're right. I think so. That's right. Thank you. So okay. And then second equality is just the base, right? You just do the base. And then last one is what? Basically, what we are showing is that you can say is that the potential outcome is independent of the AK, right? Given the current observation. So that is the SRA, right? Sequential ignorability. Then you can, this guy can be product of the two probability and then cancels. So that you have this one. Okay. And now, so we haven't really proved yet. We just, so if you look at this one to this one, we just change this one to potential outcome, and we just remove one AK, final AK, away. And now we still do the same thing here. To do the same base theorem. So I guess this one is all. So basically we can do base. And then conditional on this one, this guy is actually exists to bar. And then and then this one becomes a conditionalist. So this is also base. So I guess this is base. This is Stuba. This is base.
What should be sequential ignorability?
Which one?
The circle.
1, 2, third equality. No. Actually, I didn't really cancel out anything.
Oh,
This one just goes inside.
you cancel, right? So
No, I didn't. So this is joint. This is conditional. This is marginal. Joint marginal. Joint divided by marginal is conditional. Huh? Which one? The third one? I didn't cancel it. See, it just moved here. No cancellation. Forget about all this. Forget about this is joint. This is marginal. So joint divided by marginal is conditional. That's it. Right? So I didn't do any cancellation here. So just I obtained this. Okay. So that means what? That means I can basically write this guy. So
last one is by what? Last one is by sequential ignorability.
all right. So thank you. Right. And now last one is a sequential ignorability. And also positivity, right? So basically see, then that implies, so if you look at what happened to from here to here, basically, so this guy, so applying the same argument, you basically this guy can be changed to potential outcome, and this one have a reduced order. So that eventually can be
Expressing everything in terms of potential.
right. That's right. That's the goal, right? That is the goal. But to achieve this, I have to go through these steps. Okay. So this so that now you guys can probably see why it's better to use backward, because you basically start with y, and from y you construct v, right? You start with y, so that is a q function. Okay, so basically you use compute the q function using the data, right? You compute the q function using the data to find the optimal at the last step, and then use it to compute the value function, and then use the value function as a outcome variable, and take the conditional expectation. So you use the value function and take the conditional expectation to obtain the q function for the previous step, and then use that q function to obtain the optimal DTR, optimal decision in the previous step sequentially. So, and then until you get k equal to 1. And then once you obtain k equal to 1 optimal, then you actually, this one can be plugged in to obtain D2 optimal, because D2 optimal is a function of D1. As you can see here in the start with the toy example. Yeah, so anyway. Okay. So constructing the Q sequentially backward, right? Constructing the Q function sequentially backward is essentially called Q learning. And this value function is also constructed sequentially backward way. So this value function reflecting the expected outcome value that will result from the following optimal rules now and in the future, given the past history to thinking. Because the Q functions for the potential outcomes, so Q function can be defined either in terms of the potential outcomes or in terms of the observed data. So that is the critical part, right? So that is this is the basically the most critical part of this theory. So basically you use your optimal decision supposed to be based on the potential outcome model, but turns out that you can estimate it from the observed data. So that is the kind of idea here. Okay. So that basically, so we now, any questions, by the way? Yeah. Value function to be identified. I don't know that. Yeah, sequentially, right. I guess One thing I should one thing I should point out perhaps is that so this is the basically history, right? This is the history at case step. And then I have two things two unknown. I mean, at case history, right? At case HK, I have to decide the two things. One is AK, right? Given history, I have AK unknown, and also I have a potential outcome from the right. So this guy X K plus 1. So these two, I have actually two things here, this one and the AK, but and now I think the identification condition, the Sutuba and SRA and positivity actually makes this equality holds. But for the modeling, right? For the modeling, the actual correct model specification is very difficult problem. Usually, because it's a function of, even though the relation between y and x is y given potential outcome y on x is very nice. This is not nice, right? Non-smooth function. You have a kind of several decisions based on. So this is a function of a that creates a problem more difficult because of this kind of nature. So I think some, but this Q learning, I know that Q learning is very popular in reinforcement learning problem too. So I think they are kind of doing this conditional expectation using machine learning, deep learning algorithm. But I don't know how much they care about the selection bias. Well, so you guys can use this, for example, and see whether you can obtain. So basically finding D2 optimal is relatively easy because you basically have a local, right? For each one, you just compare T2 and then choose the one, and then use that to compute the V2. And now what you need to do is to compute the conditional expectation of the V2 given x1 and a. So that means given x1 and a, we basically want to do average. Not here. Actually, sorry. Average of compute one number. Right? Compute one number. But it cannot be just a simple average. No, right? Because you need to, what is going on here? Here, what is going on is the x2, distribution x2, given x1 and a1, right? But that distribution you can actually obtain from the sample, from the table that you have here. You can actually compute what is the probability of x1 equal to 1 given x1 and a1, right? And so use that to compute the weight, to compute in applying the weighted average, right? And that will give you basically Q1, I think, and then you should get.
But in this example, it does not matter because in this example, it does not matter because A2 are all the same, right, in each of the cell.
Actually, here it's the same, but they are different.
Oh, yeah.
Right. So this one, right. So this one doesn't matter. There, no matter what, this will be 0.4. But this one, you need to compute the conditional distribution to make the proper weight computation of the conditional expectation. Right? Because see, this one, you can see that this one is expectation of this V2 term, which is actually function of x2, because the other is a constant, I mean, given. Yeah. So, yeah. So you guys have 2 days to fit out these numbers, and then we'll move on to the next step. Okay.